the community, I guess. But I'm interested as well in sort of learning and getting the hang of it. But that will probably take some time. I'm currently just getting started with Python and all of that. So I guess just really excited to be here. I don't know if I'm the last one.
You can pass it. There's still three more. See if you can guess
Okay,
right.
I'll pass it on to Quiet Catalyst.
Oh, nope. Close. How about we send it over to Roger?
Hey guys, my name's Roger, obviously. Yeah, I know a little bit of CadCAD, still trying to figure out where to fit in the community. Joining the guys for the study group at the moment. Although I missed yesterday due to firewall issues, but yeah, that's it. Still trying to figure out stuff. And I'll pass it to Anidru.
Close enough. How's it going? So I am Anirudh, or you can just call me Ani if that's easier. So yeah, I work for Semiotic AI, and we actually partner with Block.Science, which is how I got introduced to cadCAD. I'm also out in California. So yeah, I'll be talking today about this library we've developed, this Python library to use reinforcement learning with cadCAD, but I guess we'll get to that. So I will pass it over to Tyler.
Awesome. Yeah, so I'm Tyler. I'm involved with Block.Science a number of ways. Currently working on the Labs platform, which is putting cadCAD in the cloud so that you don't have to run it locally, sort of building out a platform for the entire pipeline of modeling work from the initial prototyping and experimental development phase all the way through to the post-processing of model-generated data. And also working on the reference implementation for cadCAD, which is a from-the-ground-up rewrite to try and fix a lot of the UX problems that we've had in the past and just generally make the software more accessible. That's it.
Awesome. That's everyone. Cool. Then we don't have to waste any time. We can get to the good stuff. So, Anirudh, I think we did our tech check-in earlier today, so it should be all set for sharing the screen and everything.
Yep.
But I'll just hand it off. Yeah.
Hopefully. Let's see. Let me know if you guys can't see my screen.
All set.
Perfect. Yeah, so like I mentioned before, I'm Anirudh or Ani, whichever you can pronounce. I work for Semiotic AI as a senior research scientist. In particular, my background is in reinforcement learning, and more specifically in multi-agent reinforcement learning and multi-agent systems, which is, I'd imagine, quite an interesting area for many of you if you have an interest in machine learning or deep learning and game theory, which, at least in my experience working with Block.Science, this is sort of the area that we tend to hang out in. So yeah, I developed this library called CadR, which basically enables us to do reinforcement learning with cadCAD, and I'll talk a bit about why we need like a special new library in order to do RL with cadCAD as we get to it. But I'll probably just start with quickly like running through what reinforcement learning is. So just a quick shout out to Barlow and Danilo from Block.Science, who both took a look at this code and gave me suggestions on how to improve it, and also to Sam Breen of Semiotic, who helped point me to cadCAD in the first place. Also, if you have questions, please interrupt me. It's absolutely fine with me. So we'll start with just the basics of RL. I'm not going to go into too deep a dive. If you have sort of significant questions about RL in some sense, I'm happy to answer them. So again, feel free to interrupt. But basically, reinforcement learning is just an AI technique that we use to teach an agent, which is some sort of like machine or computer, to learn a policy that it uses to navigate an environment so as to maximize some reward function, some value function. So you can think about it like a general optimization problem. You can also think about it as, teaching your dog a new trick. You teach them to shake, and you give them a treat if they do well. And over time, they just learn that if they shake, they get a treat, and sort of teaches them something new that they can do. So in general, we formulate reinforcement learning problems as what's called MDPs, Markov decision processes, which, if you're familiar with the game theoretic literature, or controlled theoretic literature for that matter, this shouldn't be too unfamiliar, but I'll go over it in any case. So at each time step, we have some agent, and the agent is the thing that we're teaching as a reminder. And that agent is going to take some action A from some state S, as per this agent's policy pi. And pi can be a stochastic function, in which case the action is the action given the state, or it can be a deterministic policy, in which case the action taken is totally determined by the state that you're in. Okay, so once the agent takes this action, it transitions to some new state S prime as per some transition function. You can use the transition function to model a lot of different things in the environment. So for example, if I'm, ice skating, I'm not a very good ice skater, I can try to go forwards and I end up slipping, and I have some probability of just moving to the right when I try to go forward. So it can model things like that. It can also model things about, in the multi-agent sense, what other agents are doing, right? The state that we're looking at here is not just my state, it's the state of the whole environment. So if there are multiple players in this game, what happens at each time step doesn't just depend on my action, it depends on everyone's action. So the updated state is not purely a function of S and A anymore. And so there's some probability that I'm going to be able to approximate that new S prime well. So when the agent takes this action from this state, it gets a reward, right? Similar to the analogy I used on the last slide with giving a dog a treat if the dog shakes your hand. So anytime the agent does a positive action, or what we think is a positive action, it'll get rewarded with some positive reward. You can also give agents negative rewards or penalties if the agent does something that's detrimental. And you can, of course, give agents mixes of a mixture of positive and negative rewards. That's totally okay as well, although there are some nuances to how you would actually do that. Now, what we're trying to do is this optimization problem. We want the agent to learn to maximize its future return given what's called the discounted sum of returns, which is this G sub t. And this gamma term in here is what's known as the discount factor, which is essentially a constant that trades off between 0 and 1. And on the extreme end of 1, setting gamma equal 1, what this essentially means is that future rewards are equally valuable to the agent as present rewards. So, for example, if I'm going to say, I'll give you $10 today or $100 in a week, the agent will go for $100 in a week because it values that equally as highly. If gamma equals 0, it places 0 importance on future reward, right? So it's going to take the $10 today and discard the $100 in a week. And this has some nice sort of mathematical properties, which is why we use it. But also just from ignoring the math from an intuitive sense, if you're in a really risky, if you're playing a really risky game, right, you may be more risk averse, in which case you're going to push gamma closer to 0 and value the rewards that you can see in front of you rather than the potential rewards that you might get in the future. And vice versa, of course, if you have a pretty well-defined game. So Markov decision process is just defined by the tuple over states, actions, the transition function, the reward function, and the discount factor. And the key sort of idea behind Markov decision processes is that the tuple's definition at time t plus 1 only depends on its value at time t. So you don't need to keep a full history to understand what's going to happen at the next time step. And this is a property of a lot of systems. And in fact, you can get pretty far with this definition. There are generalizations of reinforcement learning. When you don't have this sort of same information, right? You might have heard of partially observed Markov decision processes, MDPs, which is a single agent game in which you don't have access to the full state, right? Like I said earlier, The state S is a global state. You have to know every single thing about the environment in order to call it a state S. If you don't, then it's an observation, and you're working with MDPs. You can generalize to belief MDPs, and then the multi-agent game is entirely different, where you start dealing with things called Markov games and stochastic games and extensive form games. So you can see there's a lot of game theory terminology here, but for now we'll just focus on the MDPs because that's sort of the classic starting point of reinforcement learning. Any questions so far? Cool. Okay, so like I said, we essentially have this maximization problem, right? We're trying to maximize, or we're trying to get the agent to maximize its return by selecting the correct policy. And so we need a way to approximate this return. This return, if we take a look again, is looking at the reward in the future, right? The agent doesn't have access to that information at any given time step. It doesn't know what reward it will get 1 time step from now, 10 time steps from now. We talked about wanting to set gamma to 0 when it's really difficult to predict the future. Well, this is a case where it's really, really difficult for us to predict out what the agent's reward is going to be 100 time steps from now. So we want to focus in and try to get and try to approximate this function in some way. And we really have 2 ways that we approximate the return in RL. Of course, because there's some uncertainty, we're taking expected values, although there are tricks you can do there. But we often use what's called the state value function or the action value function. The state value function is basically a function on just the state, and the action value function is an approximation of the return over both states and actions. Yeah, not much else to say about this, other than if you ever hear about things like Q-learning, Q-learning is going to use this action value function, Q-tables as well. That's sort of a classic reinforcement learning algorithm, I think from the early 90s. Whereas if you ever hear terminology like the advantage function, the advantage function is just the Q function minus the value function, basically the difference you get for taking this specific action versus essentially averaging across all actions. And you might hear terms like that if you are into reinforcement learning and start reading about algorithms like proximal policy optimization, so PPO. So how do we find this policy? Essentially in RL, I'm making quite an oversimplification here, but one of the dimensions along which we can divide RL algorithms is between value function learning or Q learning and policy optimization. So in value function learning, what we're going to do is we're going to try to, we might use a neural network or some other function approximator, and we try to get that function approximator to output values that are approximately equal to the optimal Q value, right? And once we get that, the policy that we want to take, the action that we want to take, then just becomes the simple problem of taking an argmax over the actions. So this works quite well if you have discrete actions, of course, or a discrete action space, I should say. In policy optimization, on the other hand, you want to learn the policy. You have some return some value function. Often you don't know that value function, so it's something that you're learning concurrently. But what you're going to do is you're essentially going to take it essentially becomes a classic machine learning problem in that you are taking steps in the direction of the gradient of the objective function. So Q-learning is quite nice because it converges faster. In RL parlance, we call that it being more sample efficient. But it has many more failure modes, and that's fundamentally just because we're not optimizing in Q-learning for the thing that we actually care about, right? We actually care about the policy, and we're not optimizing over that. In policy optimization, it's a lot less sample efficient. Basically, every time you do one training update, you have to throw away all the samples that you collect. And we'll talk about what sample collection means. Whereas in Q-learning, you can keep them till the end of time. However, it's more stable because, again, you're just optimizing over the thing that you care about. So there's sort of these 2 worlds of RL. Okay, before we move to the next section, any questions? Anything I can clarify? All right. Okay, so let's talk about the training loop, and this will start to get into why we need a new RL library to interface with cadCAD. Okay, so here's a typical reinforcement learning training loop, right? So you're going to set up the algorithm, the environment, which is in RL what we call the simulation, and a buffer. And the buffer is essentially going to store samples, right? If you think about machine learning, say I'm training an image classifier to recognize cats and dogs. I have a data set already, right? In reinforcement learning, the agent learns by playing with the environment. So I'm generating the data set in real time. I have to store that generated data set somewhere, and we store it in a buffer. And that buffer turns out to be quite important because depending on the algorithm you use, you need different types of buffers, as well as there being a lot you can do in terms of making the buffer itself a machine learning problem. Helps you with your training process. So don't discount the buffer as just something trivial. It's not just algorithm simulation, it's algorithm simulation buffer. They're really all three important components. So once we set those up, while the algorithm hasn't converged, and you can define that however you'd like, what we're going to do is collect rollouts, which is essentially have the agents play in the environment and collect information and put that information into the buffer. And then once we've collected rollouts, we will update the neural network parameters. And just keep looping this until we converge, right? So quickly, let's just expand out what we mean by rollout collection. So this is an oversimplification again, but for each episode in the number of episodes that we have for update, what we're going to do is we're going to reset the simulation and collect an initial observation, right? And then for each time step in that episode, we pass that observation to the algorithm. The algorithm uses that to output an action. And then we add that action, observation, and then other parameters that will depend on the algorithm to the buffer. Once we do that, we step the simulation forward by passing that action to the environment. And that's sort of the loop of how things work in reinforcement learning. Okay, so in RL, we typically use what's called OpenAI Gym. This is a common backend for a lot of the simulations that we run, right? And so the key thing here is that, firstly, environment.step and environment.reset are exposed. They're something that is called externally, right? The simulation is stepped forward outside of itself. It doesn't run itself like it does in cadCAD. And also in cadCAD, another difference is that the step function is a local function and can't easily be exposed. So, again, on this slide, if you look, we have this environment.reset and environment.step call. cadCAD doesn't expose those. So we can't use it with a typical gym-like interface. And that unfortunately discards or discounts most existing RL libraries, right? So for example, you can think of Stable Baselines 3, which is an incredibly popular reinforcement learning library. By default, it'll take any environment that you want, but it requires that the environment be a gym environment. So no real luck there. And you can't really adapt it. You can't wrap the cadCAD interface just because the environment.step function is not exposed. So we really do need a new library for this. So hopefully I've shared the motivation enough with you guys. I will now switch over to this GitLab link, which is where you can find our repo as well, and just take you through the example that we have there.
Hey, Ari, can I ask a quick question as you're transitioning there?
Go for it.
So you'd mentioned how, because of the nature of how the simulation runs, things that have been developed in the GIM paradigm don't cross over into the cadCAD paradigm. From your perspective, do you see that as a potential for loss of some of the work that has been developed in GIM and that might be useful in this world for cadCAD, or is it more of a just sort of an inconvenience that leads to needing to develop a new framework for reinforcement learning?
Yeah, that's a good question. So it does make it more difficult for reinforcement learning people like me, in the sense that we do have to start developing these new tools in order to use cadCAD with GIM or with RL. And to expand on that a little bit, for example, a lot of things that GIM already has implemented. For example, you can think of training against Atari, right? I think that's a classic RL problem that people tend to know about, is that teaching an RL agent to play Atari, that has an existing GIM interface. As far as I'm aware, that doesn't have an existing cadCAD interface. And so doing those sort of benchmark problems that are quite typical in reinforcement learning papers via cadCAD would still be like an extra step. You'd have to re-implement a lot of what exists. So quite frankly, the easiest thing to do would be to expose the environment.step call in cadCAD such that we can make a wrapper, basically, that allows cadCAD to have an OpenAI GIM sort of interface that all these other RL libraries could use. Did that answer your question?
Yeah, that's perfect. Thank you.
Yep. Anything else? All right. So this is just Python implementation, talking about rollout collection, which we talked about already. So I'm not really going to go back into that. This is talking about the algorithm update step, which I sort of skipped over. But for this talk, that might be interesting. Basically, the update step is just you're going to grab a batch of samples from the buffer. You're going to pass that batch through the algorithm's loss function, calculate that loss, and then backpropagate that loss. It's really a typical ML loop. The only interesting part is that you are grabbing your data from the buffer instead of some other existing data set. So nothing super complicated there. And like I said earlier, the workflow here is really do a rollout collection step, do an update step, repeat. All right. So basic information on how to install CadR. Nothing fancy there if you're used to pip. And I guess what we should do now is we should probably expand on this these steps that I've been talking about sort of abstractly, right? So we have this setup, for range, no episode, collect rollouts, update agent. Okay, so let's start by expanding out the setup step, right? So we need to set up the buffer, we need to set up the neural networks or whatever function approximator you want to use, and we need to set up the algorithm itself. So CadR exposes a buffer, basically. So you just create a buffer like this and set its max length equal to whatever you want. Typically, this is quite a high number because you have, for Q learning, you can keep samples around till the end of time, like I said. So you might want to do that. And for policy learning, you still want this number to be quite high because oftentimes there are environments that you'll run for like millions or tens of millions of time steps before you actually do a policy update. So typically this number tends to be quite high. We also need to know the size of the observation space and the action space, so 4 and 2 in this case, so that we can use it essentially to create the function approximator, right? The function approximator, if it's a neural network, needs to know the input layer size, which is the observation, right? The policy takes in some observation, and it's going to output some action, so it needs to know the size of the output dimension. So actor critic here are referring to the actor being the policy and the critic being the Q function. In particular here, we're using an algorithm called TD3, Twin Delayed DDPG. And TD3 also uses a twin critic for various sort of optimization mathematical reasons that I can get into if anyone's curious. But essentially, we just create a clone of the critic, right, with a slightly different initialization. So now we have the network set up. We move on when we set up the algorithm, right? Okay, so in CadR, the way we expose the algorithm is we always have this sort of, independent of the algorithm, we always have this sort of flow where it's cadr.algorithm name underscore agent, algorithm name underscore optimizer, and algorithm name underscore loss. Right, so you can see for TD3 here, we have TD3 agent, and the inputs here are going to depend on the algorithm that you're using, of course, so I would recommend reading the documentation for that. So we expose TD3 agent, TD3 optimizer, and then TD3 loss, and that sort of defines our algorithm. Okay, so with the algorithm set up, we need to set up our simulation as well. Like I said earlier, if you do have access to a gym environment, I'd encourage you to use a different library, like a different RL library, which is much more mature than CadR, probably stable baseline 3 for most purposes, to be honest. But you know, we're going to have to set up certain special components for using cadCAD in an RL setting. So the first thing to know is that the T parameter in cadCAD refers to the episode length in an RL setting, right? So how long a game is going to go on for. The N parameter is for Monte Carlo simulations. It should probably be set to 1 for most RL algorithms. And we can also use the M parameter to specify any constants that we want to provide. So for example, if we want to use a specific time step size, we could pass that in here. M is also technically used for Monte Carlo sweeping parameters. So you can do that if you want, but in theory, the RL environment should be like, even if it itself is stochastic, you're not really using it to run Monte Carlo simulations. You want something stable with an agent, which an agent can train on. Okay, so we'll want to set up the partial state update blocks. And so you're going to have to start passing in some stuff explicitly related to RL. And so firstly, right, your policies need to translate the output of your agents to the input that cadCAD expects. So here we have this agent.action call, which is taking in some observation and returning an action. And because of you know, the syntax of the partial state update blocks, you should return this as some sort of a dictionary that maps whatever you want to call the key to the value action. You do the same thing, for example, for the agent observation. So you'd create one or more of these functions for each other key in the buffer, right? The buffer we talked about earlier that's storing samples from the environment. So then if we put all the pieces together, we might have a partial state update block list that looks like this, right? So we have the policies. This is just a single agent, so we're just going to call it agents and pass it the cadCAD RL policy example, this function. And then we have all these variables referring to the states, the rewards. Agent done is essentially whether the agent has reached some sort of terminal state. Agent observation is just an observation of the state, and then agent action is the action. So that's pretty much everything that occurs outside of the training loop. It's pretty straightforward, but you have to define all of these functions for yourself. All right, so in the training loop, we talked about earlier, we have rollout collection, update, and then you could do some sort of early stopping if you don't just want to run for the entire number of episodes. So what you're going to do is you're going to create a random initial state, initialize the state with certain values, right? So your initial reward is going to be 0. Initially, your agent is probably not done playing in the game. It would be kind of strange if it were. So just these sort of basic things. You set up a cadCAD experiment, append all the configs that you've created, and then do just normal running, right? All right. So system event. Yeah.
Let's see. Your early stopping. So if you've reached convergence criteria, you can break out at that point.
Exactly.
Okay.
Exactly. So system events is going to contain all of the variables that we want to track over time. So now we're going to use it to populate our buffer, which we then use for the algorithm update step, right? So we're going to do this via buffer.append. And again, what goes into the buffer, what comes out of the buffer is going to depend on the algorithm. So pay attention to the documentation here if you're not familiar with RL, right? It's not sort of just a generic thing. So buffers are going to contain observations and next observations for TD3. So we have to do this thing where we zip the system events all the way to the last element -1, and then skip the first element and go all the way to the end, and that's how we basically get the next observation. But yeah, we just loop over that and append each of these samples to the buffer. And now that we have a buffer, it becomes pretty straightforward to call, TD3_updates. So that's basically what's going on here. You can pass in some extra hyperparameters that you might care about here, such as batch size. And that's pretty much it. I'm flying through this example. If you want like a more concrete example, and if you go over to our code, we have this example predator-prey, where there's basically this predator that's trying to hit some sort of like X marks the spot sort of thing. So you can sort of see a more full example here. I would start with main.py and go through this. Hopefully it's decently well commented for you. And you can sort of peek into things that you might, have questions about, like how do we specify the pursuer? Yeah, that's about all I've got. Does anyone have questions, things that I can clarify, or just like not even about CadR? If you have general RL questions, I'm happy to answer.
You talk a little bit about the library dependencies. I thought I saw a reference to PyTorch in there. Are
Yeah.
there other jacks or other things that would help with managing the gradients and the optimization process?
For most cases, you're probably pretty okay with PyTorch. Yeah, we didn't implement a TensorFlow equivalent, so it only really works with PyTorch, I would say. Of course, there might be other things that you want to, might be other dependencies that you want to install for your own sake, but we don't sort of provide the ability out of the box to do things like inspect TensorBoard, right? That's fairly easy to hook up for yourself through whatever your main.py is, so that's sort of left to the individual. But there are certainly other libraries like TensorBoard that could be helpful in training.
Thanks.
So you wouldn't actually run this with cadCAD. This is like a new version of cadCAD, basically.
No, not quite. So we do actually run this with cadCAD.
Oh, okay.
The purpose is to, so if I run over to main.py here, we are actually importing all the normal stuff from cadCAD. And we do actually, set up the experiment and then execute that single run.
Got it.
So we're using cadCAD as sort of the back end to step the simulation forward by one episode. And everything outside of that is sort of CadR RL related stuff. Yeah.
Right. Okay. Cool.
Cool. I'm not hearing other questions, so I will.
I have a general. So that the repo
Yeah.
is open source. Is that correct?
That's correct. Yeah.
Would you be able to share the link?
Yep. Absolutely.
Um,
Where should I post that? Does anyone know? Sorry, I'm not like a Discord user.
How about the? Is there a text channel for a community call? No. Throw it in the TE cadCAD study group.
All right.
Yeah.
You got it.
Nice. Cool.
Oh, I just realized I linked you to main.py. link you to the repo itself
Okay,
instead.
yeah. Nice. Awesome. And maybe this is actually a question for Tyler. Tyler, I don't know how much you were tuned in the first half of this, but I think so. It sounded like one of the main reasons for building CadR was that cadCAD, I guess cadCAD legacy at this, as we would call it, would be it doesn't actually expose one of the steps or some of the steps needed for reinforcement learning. Have you heard anything about that discussed for cadCAD 1.0 development? Maybe he's not here. All good. I'll ask him later. Okay.
Ali, have you looked at cadCAD by any chance? That's it has exposed every step. It's got hooks that you can hook into to do specifically these type of things. You need to update variables and stuff through the steps.
I have not, no. I don't know if Anirudh, if you have.
I'm sorry, there's a vacuum going on outside my apartment. I didn't hear that.
I was saying, have you looked at radCAD? It's a different implementation of cadCAD, and it actually has hooks that you can hook into in every step and take control of what you need to do and adjust things and update stuff. It's actually quite handy. It's worth a look.
Yeah, so I did take a look at that with Barlow and Danilo. I don't remember why exactly anymore because it's been a couple months, but I remember it for some reason it just didn't work out.
Okay, cool, thanks.
What are the plans for future development?
So currently this is sort of provided as is. We're not developing this anymore. If you guys have things that you would like to see implemented, you're more than welcome to submit feature requests or PRs, but as it currently stands, it's in a usable state for us. So yeah, no real plans right now.
Awesome. Very cool. Any other questions? Super interesting presentation. Actually, I was just remembering we actually had someone else from this project called Block.Science who also presented on reinforcement learning in agents in cadCAD. I'll have to send you see if I can find the recording of it on YouTube somewhere. But yeah, I guess it was a slightly different use case, but could still be interesting. So
yeah, that'd be
few
awesome.
people out there working on reinforcement learning. So very cool. Nice. Is there anywhere that we can look to keep up with the project? I guess maybe. I mean, obviously we can keep an eye on the repo, but for semiotic AI, was that it, or semiotic?
Semiotic, yeah.
Semiotic AI. Okay. Yeah. Is there anywhere we should check out to stay up to date on any developments there?
Yeah, so you can always keep an eye out on. So that repo that I linked you to, it's hosted on Semiotic's public GitLab. Mm-hmm. So anything that we open source or decide to share will definitely be put up there. So yeah, I think that's probably where I would pay attention. And like I said, if you guys want any extra features or something, feel free to submit requests or even just submit a PR if you want to take a shot at implementing it yourself.
All right. Sweet. Well, I think that might be all for today then. Did you have any last comments, Anirudh?
Nope, all good for me. Thank you all for your time.
Sweet. Yeah, thanks for presenting, and thanks everyone for joining.
Thanks for sharing that.
Yeah, really awesome. Interesting.
Great stuff.
Cool. Well, we will see you all hopefully next month or around elsewhere in the community, token engineering commons, etc. So we'll see you around. Bye, everyone.
Bye. Take care.